In this video, we're going to continue our discussion of regression in R. We started with simple linear regression. Now we're going to keep going into multiple linear regression. So MLR. Now we can incorporate multiple variables into our model pretty easily. So I'll have my mod, and I'll call this the MLR mod. And I'll still use the same LM command. Miles per gallon is still going to be my outcome. And I'll still be looking at the quarter of a mile time in seconds. But now I'm going to add the weight of the car as a variable that I also want to account for. So this is going to account for two continuous independent variables. Now we showed how to construct our plots previously to assess the assumptions, but there's actually a quicker way. We can do the plot command and then give it our model, give R our model. I'm going to say which equals 1 and 2, or 1 through 2, because I just want to ask for a couple of the plots. And R will actually, by default, create some pretty useful plots. I have my residual distribution plot here, which shows, this looks pretty good. This shows that there may be a curvilinear relationship, but that's not too bad. I think it looks pretty good. And then if I hit enter, I see that QQ plot that I made before too. So actually, this is a really handy way to make these plots pretty quick. We talked about how to make them yourself though, because sometimes these plots come with some weird defaults and I don't particularly prefer them. And also this QQ plot from CAR is pretty handy because we have those built-in confidence intervals and we can just see if anything is outside of that blue shading. So that's pretty nice. Now, the way in which we do our assessment of the model, remember, once we have significance tests and once we have the assumptions that we check, we actually go in a bit of a different order. So the first thing that we do is we fit the model. The second thing that we do is check assumptions. So this is what we do before we ever look at significance tests or before we interpret parameters. We check those assumptions, and then, and only then, if those look good, we can go on to the next step, which is not even to interpret the parameter estimates yet. The next step is to check significance. And then, if significant, interpret parameter estimates. So in this case, I see that both the quarter of a mile time in seconds and the weight are both statistically significant on miles per gallon. Quarter of a mile time is positive. This indicates that as quarter of a mile time goes up, the miles per gallon goes down after accounting for weight. And the weight is negative, indicating that as the weight goes up, the miles per gallon goes down after accounting for the quarter of a mile time. All right, so that's how we use multiple variables in regression in R. Pretty easy. We can also drop in categorical variables in R. So if I look at the structure of the MT-CARS data set, one of the ones that I want to drop in is AM, which stands for automatic and manual. Now I note that right now it's read in as a number. Now it's read in as a binary, so I could use this variable as is as a binary classification because it's already dummy coded. But I'm going to show you how to create a factor in R so that R takes care of all the details. And this method will work even if the variable isn't already dummy coded. So I'm going to add a new variable to MT-CARS. What I'm going to call it is cat underscore AM, standing for categorized automatic manual. The command that I'm going to use to create a factor or a categorical variable in R is the factor command. So what variable do I want to factor? Well, I want to turn the MT-CARS AM, which right now is a number, 0, 1, into a factor. Now, I have to give R two pieces of information. What is currently in the variable, and what do I want it to go to? So levels tells R what is currently in the variable, and what is currently in there is 0 and 1. Labels tells R what I want this to go to. So 0 represents automatic, and 1 represents manual. Incidentally, whatever is the first category is going to be the reference group that I do my test to compare to. So if I wanted something to be different, let's say I wanted manual to go first, I would have to change the order not just of the labels, but also of the numbers. So I would write these numbers in order 1, 0, and then write manual automatic. So it's really, really important. You can put these in whatever order you want. Again, reordering them sometimes is a handy feature. But it's really important that whatever your first number is, in this case 0, aligns with whatever your first label is, in this case automatic. Because if you mess that up, if you like reordered the labels without reordering the numbers, you'd be telling R that 0 represents a manual, and that's not true. So you'd get really confusing. In fact, you'd get completely wrong results. So be really careful about that. But once I have this in, once I feel comfortable with it, I can go on and run that, and then I can create my I'm going to call it cat mod for the model with my categorical variables. I'm still going to be looking at miles per gallon, and I'm still going to be looking at the time in seconds to do the quarter mile. But now I'm going to be also accounting for the categorized version of automatic or manual. So maybe I think the transmission type has an effect on the miles per gallon. That's going to be empty cars. And just like before, what's my first step after I fit the model? Well, my first step is to check the assumptions. So cat mod, plot cat mod, and actually I messed up here. I didn't tell it which graphs I wanted, so I'll say which equals 1 and 2. And I'll hit enter. That'll show me this first one. Everything looks pretty good. There's a weird little clustering. I don't particularly like these labels in R. There's not a ton of variability on the left side, but I'm not too worried about it. There's not a lot of data over there anyway. And then my QQ norm actually looks really good. So both of these look fantastic. I feel pretty comfortable moving on to the next step, which is checking the statistical significance. Now, and I see I have an extra comma here, so that's R is yelling at me about. All right, so to check my statistical significance, I'll do summary of cat mod. And again, before I look at any of the, actually I'll clear my screen and run the summary here. Before I look at any of the parameter estimates and interpret them, first I'm checking their significance. So I see that the quarter of a mile time in seconds was significant, and the automatic versus manual is significant. So let's interpret these. I'm not going to touch the quarter of a mile time. We've already interpreted that a couple of times, but I'll focus on this one. Now in R, I have the variable name, and then it's kind of annoying, but R just kind of writes the level of the variable that it's using for the binary coding right after it. So catam manual. So what this is saying is we're looking at the manual group, and we are comparing it to the reference group. Now, in multiple variables, the reference group is the one that's not going to show up in the model. So what's not showing up here? Well, automatic is not showing up here. I can also go back to the factor where I made it, and the first category is going to be treated as the reference group. So what this is saying for manual is that manual is statistically significantly different than the reference group, in this case, automatic. So manual is statistically significantly different than automatic. The parameter estimate is telling me what direction is manual different from automatic in. So in this case, I see manual is +8. It is 8 different, 8 higher, +8, 8 higher than automatic. 8 higher what? Well, 8 higher miles per gallon. So manual has higher miles per gallon than automatic in this particular case. And I see again that this is statistically significant, and this matches what I know about cars. Manuals tend to get better gas mileage, and after accounting for the quarter of a mile second, manual looks like it actually gets almost 9 miles per gallon better than automatic gas mileage. And again, I feel it's statistically significant. Now, if I wanted to come up with a reasonable range, I could do my confint and give it my categorical mod to get the reasonable range of values. So reasonably, manual might only be 6 miles per gallon better than automatics, or it might be up to 11.5 miles per gallon better than automatics. For me, these are pretty big numbers anyway. Like 6 miles per gallon, that's nothing to sneeze at. So maybe if I'm looking for a high miles per gallon car, Manual is a good option to consider selecting. All right, so the last thing that we talked about doing in our notes is dropping in a curve. Now there's a couple of different ways to do this. Curvilinear. And I suck at spelling, so maybe that's not how you spell curvilinear. Anyway, maybe Art can tell me. Nope, no idea. Okay, so again, there's a couple of ways to do this. I'm going to show you one pretty easy way, and I'll tell you why I like the easy way as well. It makes for some easier graphing. So the first thing I'm going to do is plot a relationship. So I'm going to look at miles per gallon, and up until now I've been looking at the quarter of a mile time in seconds, but now I'm going to just look at the relationship between miles per gallon and weight. And when I look at this, I can see that the miles per gallon time and weight, as weight increases, miles per gallon decreases, but it kind of levels off here. It seems like maybe if I just fit a straight line, that wouldn't be particularly appropriate. Maybe there's a bit of a curve here. Now remember, if I fit a curve, I can look at the significance of the parameter estimate for the highest order polynomial, that is the squared term if I try to square it, or a third to the third power, the cubic term if I try to cubic, to see if that level of curve is supported statistically. So in this particular case, I'm going to go on and fit my model, MPG, and I'll call this my curve mod, based on weight and data equals MT cars. Now the question is, how do I change weight from being a linear term to being a polynomial? And the answer is I use the command poly. So instead of just writing weight, I'm going to write poly, parentheses, and then the variable, and then a comma, and then I tell it to what power do I want weight to go up to. So in this particular case, I want weight to go up to the second power. So weight's going up to the second power in my curved mod, and I can go on and, I could do the assumptions checking. I'm actually going to skip over that for now, just for time's sake. I am going to look at the summary, and I see that the second order mod looks like it's statistically significant. So that is, the squared term looks like it's contributing something. Again, I don't really look at these, because even if these weren't significant, I'm not going to take them out of the model anyway. I need them if I have the squared term. And the parameter estimates aren't particularly interpretable. One of the reasons I like doing it this way is if I wanted to fit a model to the third power, I could do this really quickly and just see, does a model to the third power work? What I see looking at a model to the third power is looking at this highest order term, the term raised to the third power. It's not statistically significant. And what this tells me is that I don't really need to go up to the third power. So what I would do if I had this model is I would drop it down by 1 power. So I'd go from 3 to 2, and then I'd redouble check the highest order term. So in this case, the highest order term is squared. I'd recheck that. Oh yes, this is statistically significant. Okay, so I keep it. It does benefit from having that level of curve. So it didn't benefit from having a third power level of curve, but it did benefit from having a second power of curve. All right, so how do I draw a curve onto this line? Well, this is kind of what I like about using the poly command. What I can do is I can use the curve command. And then in the curve command, this is a little tricky, so let me walk you through it. I'm going to actually predict. So what the curve command does is it does a whole ton of predictions. So I'm going to give it my curved mod. And then I'm going to give it the data frame, so new data equals my data frame. Remember, we always have to give predicted data frame if we want to predict something. And then I'm going to give it my independent variable, and I'm going to say equals x. And this is one of the weird things about the curve command, is it's going to fill in x with a whole ton of different values to kind of plot a little line that goes down and down and down and down and down. So X is what it's going to fill in with where do you want me to put points on this line. I tell it from where I want it to go from. Where do you want to start the curve from? And I want to start from the smallest point in MT car's weight. So I'm going to start from the smallest weight, which is just the minimum weight. And then I want to go to the maximum weight. Last but not least, if I just ran this, R would plot the curve, but it would erase my data. So instead of erasing the current plot, I want to add it to the current plot. So I'm going to type in add equals true. Oh, and it looks like I'm missing a parentheses here, so I want to figure out which one I'm missing. It looks like my predict, I accidentally deleted a parentheses at the end of predict, so I'm going to go in and add that parentheses in. And then when I type in the command correctly, I can see that this curve looks nice and pretty, and it goes on my plot. Actually, that looks pretty darn good. Just for kicks, I'm going to show you what the third power curve would have looked like. So I'm going to raise this to the third power. And when I add that on, you can see that the curve to the third power, honestly, I'm going to zoom in here, it really doesn't look that different at all from the curve of the second power. Like, I can hardly tell the difference between these. So this is probably why that third power curve isn't really doing much for my prediction. I've never actually done this, but let's try doing a poly of 1 and see if this runs. Looks like it does run, and actually what we end up getting is just a straight line. And I can see that my curves are looking pretty different from the line. So if I just did this line, up at the top I'm seeing the data points are all above. Down below I'm seeing the data points are all above. In the middle I see they kind of drop down. So I could see how just a line would maybe not be appropriate, but a curve actually looks like it fits pretty good. That said, I can't really tell the difference between the quadratic curve, the curve raised to the second power, and the cubic curve, the curve raised to the third power. So I'll use the simpler one, the quadratic curve, and say that that seems to fit pretty well. All right, this has been a breakdown of how we can utilize multiple regression using R. I think, depending on where you're at in this course, this may be our last video, so I hope you enjoyed it. I hope you learned something. And as always, please feel free to reach out if you have any questions.